Let's learn about solution sets to systems of linear equations. Let's begin with the definition. A system of linear equations is consistent if it has at least one solution. Otherwise, we call the system inconsistent. So what are the options? We have a system, and it can either be consistent or it can be inconsistent. If a system is inconsistent, it clearly has no solutions, by definition. On the other hand, if it's consistent, it has solutions. And there are two cases. It could have one solution, or it could have more than one solution. In fact, we will see if a system has more than one solution, then it has automatically infinitely many. Let's begin with an example. Here's a system of linear equations. The first equation is x1 plus x2 plus x3 is equal to 1. The second equation is 2x2 minus 6x3 is equal to 2. And the third equation is 3x1 plus 6x2 minus 5x3 is equal to 4. If we want to put this system into matrix form, we simply select all the coefficients and put them into a matrix, making sure that the right-hand sides all go into the augmented matrix as well. To solve a system of linear equations, we use elementary row operations to transform it into reduced row echelon form. I'll quickly demonstrate that in this example. As a first step, I try to create zeros underneath this 1 up here. So all these two entries I try to make equal to 0. The first entry in the second row already is 0, so all I have to do is make this 3 here into a 0. To do so, I multiply the first row by 3 and subtract it from the third row. And we see that I now created a 0 here in the front. The second entry consists of taking this 6 and subtracting from it 3 times this 1 right here. So 6 minus 3 is equal to 3. Next, I have minus 5. I subtract from that 3 times 1. That gives me minus 8. And similarly, on the right-hand side, I start with 4 and subtract from that 3 times 1, which leaves me with this 1. I also divided the second row by 2, which created this 1 right here. And I'd like to now create a 0 underneath it. And in order to do so, I take the third row and subtract from it 3 times the second row. I take this minus 8 and subtract from it 3 times negative 3. And finally, I take this 1 and subtract from it 3 times 1. And end up with negative 2. My matrix is now in row echelon form. I have zeros all underneath here. But I actually want to bring it into reduced row echelon form, so I also want to create zeros here and here. In order to get this 0 right here, what I did was I took the first row and subtracted from it the second row. Finally, I would like to create zeros here as well, so I used this 1 in the last row to subtract 4 times the last row from the first row to get this 0 right here, which gives me this 8, and also to subtract negative 3 times the last row from the second row, which gives me this 0 right here, and this negative 5 right there. My matrix is now in reduced row echelon form. And just a quick reminder, a matrix is in reduced row echelon form if it satisfies that rows with all zeros are at the bottom. In this case here, we don't have such rows. The leftmost non-zero entry of a row equals 1. That's the case overall here. This is the leftmost entry in this row, and this one is in the second row, and this is the one in the third row. These are all the leftmost non-zero entries, and they're all equal to 1. The leftmost non-zero entry of a row is the only non-zero entry in its column. That's also the case. So this column here doesn't have any other entries. This column doesn't have any other entries. This column doesn't have any other entries. And finally, the leftmost non-zero entry of a row occurs in a column to the right of the first non-zero entry in the preceding row. That is also the case right here. This one is to the right of the first one, and this one is to the right of the next one. Here again is the reduced row echelon form of the system that we just came up with, and we can read from it the solution. We know from the first row that x1 needs to be equal to 8, the second row dictates that x2 be equal to negative 5, and the third row gives us that x3 be negative 2. The system has a solution, we've just found it, and therefore we call the system consistent. In addition, there's only one solution, so we say that the solution is unique. So we found one unique solution. Geometrically, we can visualize what's happening here in a system of equations that is consistent and has a unique solution. Each equation in this case has 3 variables. It's a linear system with 3 variables and therefore defines a plane. So each of the 3 equations in our system defines its own plane, and we're looking for a point that satisfies all 3 plane equations at the same time. In other words, we're trying to figure out whether these 3 planes all intersect in one point. In the case of a consistent system with exactly one solution, that is indeed the case, as you can see in this example drawing right here. So we have this one point in which all 3 planes intersect. There are many other possibilities for 3 planes to not intersect in one point. They could intersect in more than one point or not intersect at all. Try to think about possible configurations of planes that could be happening. And we'll talk about those in future videos.